Hello, everyone. My name is Tirtha. I do hear music in the background. Is that fine? Hello, everyone. My name is Tirtha. My name is Tirtha. I'm a senior research scientist at the Robotics and Autonomous Systems Group at the CSIRO. My background is in motion planning. My name is Tirtha. I'm a senior research at the CSIRO. All right. Is this working now? All right. All right, so today I'll be talking about climbing robots, why they're an interesting robotics platform, what are the open challenges that we would need to solve to bring them to fruition, and what are the applications that they might be useful for. So let me start by talking about field robotics for a bit. So field robotics has been becoming ubiquitous for a very long time. And we do have high TRL platforms that go around in different domains, different environments, and perform fantastic tasks. Here are some of the platforms that I'm showing you. There are aerial platforms that do biodiversity studies. There are marine platforms that does Great Barrier Reef monitoring. Self-driving cars are a kind of field robotics in themselves. And also you have industrial robots which can go around and do industrial inspection and remote operations. So the main challenge of field robotics is basically trying to adapt itself to the environment they are in by solid algorithmic, sensing, and computational tools. Now, so what are the limitations? If you already have aerial platforms, ground platforms, underwater platforms, what are the kinds of platforms do we need? Do we really need any other kind of platform? So the question comes down to a problem of inspection. So if you take a task of inspection, if you look at the bridge, so infrastructure is everywhere, and one of the key tasks of maintaining an infrastructure is to do inspection. Right now, we find that robots are being used for inspection quite a bit and for good use because they are performing dull, dangerous, and dirty work, which is the mandate for robotics in the first place. But if you look at this picture, you can see that the structure itself is quite complex. And so even though you can have drones which can do remote operations, which can do remote sensing, you can actually go very close to the structures. But if you look at the underbelly of the bridge, you'll find that the structure becomes really complex. And one of the key areas where there's a lot of corrosion and there's a lot of challenges is not necessarily the exposed surface with a wide surface task, but also the nooks and crannies where some kind of faults and high stresses develop, right? So often we find that people have to climb up or rappel down in this case and reach those unreachable surfaces to either do close range inspection because of the proximity to a complex structure or to do contact measurements. And this is just for inspections. If we talk about monitoring and repair in the future, of course, you have to interact with the environment, and then you have to go and probably do some abrasion or welding or some kind of repair work, right? So you do need not only remote operations, but also close range and contact operations. And in those kind of environments, in those kind of tasks rather, it's very important to have a robot that is in contact with the structure, can hold on to the structure and perform the tasks, right? And hence the climbing as a capability becomes really interesting and important. And if you think about climbing, when I talk about climbing, I'm talking about locomotion with controlled adhesion. So these kind of problems appear in many different domains, right? So if you want to do sample collection for a cave network, there will be probably 60 to 70% of the information you can gather by using a drone. But if you want to do sample collection or do want to do biodiversity studies, you do have to get a contact either through a manipulator arm, which is sitting on the drone, or by sending a person and doing some sample collection, right? So in those scenarios, it's important that we actually be able to send robots in really tight and narrow spaces where humans can't really fit into. And the same is the case with industrial inspection. So you have wide range environments, but they're really complex and sensitive equipment where we need to do an inspection. And often these are really hazardous environments where we really don't want to send humans in the pathway, right? So having an inspection platform that can go close range and do vibration sensing or can do paint thickness measurements becomes important. And interestingly, if you think about asset management in space, in zero gravity, for example, in the ISS, if everything is falling, the only way of locomoting is to actually grab onto the surface and move. You don't have surface traction without having proper adhesion. Yes, you can have free-flying platforms, for example, Astro B, which does controlled thrust measurement, does a controlled thrust to actually move around through the internal surfaces for ISS, internal volume of the ISS. But if you want to do close proximity contact, you do have to grip and move. So even normal walking in space becomes the act of climbing. And you can see that when the astronauts do moonwalk, spacewalk, they actually have to grab onto the rails and stuff and look. So the challenge of climbing is fundamentally the challenge of locomotion with controlled adhesion. So what constitutes a really nice and solid and versatile climbing? The challenges that we face when we actually expose this complex task is that of mobility. So really have to think about how the platform can move around in complex environments. On the right, we show one of our CSIRO's climbing platforms in a typical industrial mock-up environment. So you do have support trusses, you have low clearance, you have obstructions, you have repair work that has been done on the structure, and often these are not modeled into the blueprint. You do have portholes, which are for access and maintenance. So the robot actually has to understand its environmental characteristics to be able to walk over that. Of course, one of the key challenges or the mandate for the climbing robot is not to fall, right? So it has to have robust adhesion. A climbing robot with really low adhesion is basically a falling robot, right? So we don't want jumping robots often. And whenever the environment becomes really complex, it's very important to have a proper perception pipeline that enables the robot to understand really where the structural components are, what are the adhesive capabilities of the environment, so that it can take that into account to plan its locomotion, plan its leg movements or body movements, so that it does not, it can perform the task, but it also does not damage the environment. So to address these three challenges, I'll actually present some of the approaches that we have been using there. These approaches are not necessarily the start and end of all approaches, right? So there are so many different algorithms that are available in the world, and there are state-of-the-art techniques that other people in the labs are doing as well. But I'll just give an intuition of what are the challenges that we face and what are the solutions we, as our group, has followed. So we have built a robot, we call it magneto because of magnetic feet. So it has 3 degrees of freedom per leg, and it has 4 legs, right? So it doesn't have to be this particular configuration. You can think of 6-legged, 5-legged, more degrees of freedom per leg, but this is a representative platform that we're talking about. You at least need 4 legs if you want to move reasonably well, because with 3 limbs, you get stable contact. With 2 limbs, you really have dangling contact, so that's not really very useful. So if we start looking at the degrees of freedom that this robot has, it has 4 into 3, which is 12 degrees of freedom, 12 degrees of actuation, rather, in a high dimension. So it actually creates a high dimensional space in which you can actually perform control. So you not only have 12 degrees of freedom, 12 degrees of actuation, but you also have, for each of the actuation, you can actually add the velocity of the joints, or the acceleration of the joints, or the torques associated with that into your space. So it easily becomes a really high dimensional system. The thing that challenges, that makes it a bit more challenging is not just the degrees of freedom, but the constraints that go with the degrees of freedom. So for example, if you look at the bottom task, the robot is actually doing an incredible task of moving through a really complex constrained task that it has been given. So it's walking on beams. These beams are really narrow beams, so the robot has to step on it reasonably well, but it has to deal with the protrusion that's coming in front of it. So it has to squeeze its body, make sure that it's able to move across this protrusion while it maintains a compressed form factor, and then come out, right? To do that, you have lots of constraints. You have the constraints of contact management, you have the constraints of the kinematics of the legs, and of course, you have the constraints of collision with the surfaces. And it's interesting because some of the surfaces would provide collision to the body, whereas the same surfaces in a different form factor would provide support to the structure. So to differentiate between what constitutes a collision and what enables a support structure for the robot to step over becomes an interesting challenge. If you look at the structure of the environment, usually we are looking at the structures which are generic 3-dimensional surfaces, right? So it can even be discontinuous surfaces. Whenever you have trusses and stuff, you have to step over one beam to the other. That's basically what I mean by discontinuous locomotion. But if you look at these 2 different configurations, these are very different. So the kinematic constraints that are put on the robot in these 2 environments is quite different. The picture on the left actually shows that the robot has 2 legs on a very tight beam, but they're facing each other, right? Which means that there's this internal forces that the robot has to balance. On the right-hand side, on the picture, you see that there are 2 legs walking on a particular plane, and the other 2 legs walking on a different plane. So these are non-planar structures, which means that the resolution of the geometry as well as the resolution of the contact forces becomes important. So overall, it becomes a really constrained motion planning of if you have to allow this robot to move in this kind of surfaces, of course, in an autonomous fashion. Just to summarize, we have high dimensional configuration space, we have kinematic as well as dynamic constraints because the robot has some weight and it has some mobility restrictions. It has maximum torques that this motor can hold, and of course, a maximum limit of forces that the magnets can actually support. And then it has contact constraints, which means that at any point, it has to maintain specific contact, right? And gravity is not a friend here. It's trying to break the contact in different environments. So if you put these things together, the feasible space of solutions is a really, really tight manifold in an overall dimensional space. And finding this tight manifold becomes really challenging. And that's one of the main issues whenever we have to do motion planning for this. So one of the approaches that we have explored, and I'll give a brief overview, and this is a bit older work, so much better algorithms are currently available. But if you think of the high degrees of freedom, let's look at a simple manipulator-like space, right? So if the manipulator is moving in a workspace, it can be represented in the configuration space, which is the joint space, by a tuple. right? So if you have 3 degrees of freedom, if you write these 3 degrees of freedom as the joints, J1, J2, J3, or theta 1, theta 2, theta 3, this becomes a configuration space, right? So any movement in the workspace can be changed to a movement in configuration space. As for those of us who are familiar with the motion planning tasks, one of the challenges we have to deal with is that the structure of the configuration space is not known a priori. So you have to do some kind of sampling. So if we can map individual body poses to a point in higher dimensional space, then we can actually create a network of poses. Now, interestingly, once we have a graph structure that captures this network of poses which are feasible from one body pose to the other, we can actually decompose that and start looking at combinations of configurations in the workspace by voxelizing it, and enabling the validation of those unified voxelized space in the workspace into a single point in or a neighborhood of configuration space. So just to give an example, the voxels on the left, or the squares on the left, actually tells you all the spaces that in a specific resolution is considered to be in collision with the body, right? So when we convert that into the C space, we find that that particular configuration actually corresponds to a single point in the graph. If we are able to capture this one-to-one mapping, of course, it may or may not be one-to-one mapping. If you are able to capture this mapping between the workspace and the configuration space, we can then enable and identify the whole body or whole family of configurations which are in collision with a workspace obstacle. For example, if there's a box in this robot arm environment, it may induce a set of body poses for the manipulator arm, which can be captured in the C space, right? So the joints in the configuration space graph, the ones in the red, they are identified as collision space, as collision joints, which means that if you want to do a planning, you can convert that. If you want to move the robot from one point to the other, you can actually convert that problem into a graph search problem. And then once you have knowledge of which of the nodes of the graphs are feasible and which of the nodes are not non-feasible, you can prune your graph and then run a simple A star or depth first or any other kind of graph search algorithm to figure out what is the shortest path. And once we are able to map that back into the workspace, we can actually see the robot moving in that particular trajectory, right? So that's the basic idea behind dynamic programs. By having this mapped environment cached, we can actually do a runtime query on the C-space graph. So now, as I was mentioning, we also have the constraint of contacts, right? So when the robot has to climb, it has to make sure that it remains in contact. So one way to expand this concept is to incorporate an additional metric into the graph by saying which of these configurations of the body has a contact or a feasible contact in the C space. So if you can mark those graph nodes by having feasible or infeasible contacts, depending on the environment, we can turn those flags on and off, and then we can change the structure of the graph itself. So if you take an example here, the workspace, the purple color here actually shows basically a point where the leg is going to be in contact, and then the blue color shows the body configuration, which is captured by the workspace, right? So if we have an environment with the robot sees with this local perception, you can actually discretize this with some resolution epsilon by a set of voxels, or in this case squares, where we can map feasible contact configurations into the C space. So once we know what the contact configurations are, again, movement then becomes a problem of graph search within those sub-contact configurations. And if we know which the contact configurations are, and if we know what the penetration model is of the environment, so you take the surface of the point cloud and say that those surfaces enable you to sit on the contact, but then if you penetrate deeper, those are collision points. You can actually maintain what are the contact configurations, and you can maintain what are the penetration or obstacle configurations, and based on that, you can prune your graph and do a tree search. By using some of those concepts, we were able to run a basic planner for 4 degrees, 4-limbed platform, 3 degrees of freedom. And we find that we can get reasonable results, interesting results for the robot to move forward. Of course, this is not optimized, and we will find that when I show you the videos, it's the movement is not optimized. So it's just jumping in a very discretized manner. To make these things work reasonably well on a real robot, we have to do some trajectory optimization or body configuration and plan pruning. But just to show that by representing the problem in a compact fashion in a high dimensional space, we can actually map and gather the information from the workspace, cache it into the configuration space, and do a search at runtime to get reasonably elegant solutions. And in this case, the robot ensures that its limbs are always in contact. At least 3 limbs are in contact, and it jumps between contact points to contact points. Right? So even for a configuration, or even for a structure on the right, which is really, it has a lot of trusses, a lot of possible configurations that the robot has to step through, you can find that the robot actually identifies a sequence of footholds. The footholds are shown in red, and corresponding body poses that allows it to walk. Right? So these form some of the fundamental solutions that need to be built up upon. Second problem is that of adhesion, right? So yes, we have contact. In the previous example, we saw that the contact, when we say we have contact, we assume there is infinite forces, and once the leg is close to a surface, magically it just sticks to it. But in real world, it's hard, right? So we have to maintain a reasonable contact force. We have to move in such a way that the body configuration allows the contact movement. So you can't move into a scenario where, because of the contact constraints, the body movement does not happen. So in this case, the robot, just to mention the physicality of the robot has permanent magnets on its feet. And what it's doing, it's actually turning on an electromagnet which demagnetizes the magnetism. So it has a permanent magnet which has a permanent magnetism, but it has a coil around it. So when the electromagnet is turned on, it cancels out the magnetism of the permanent magnet, and the robot is able to decouple. So this is called permanent electromagnet, and the advantage of having a permanent electromagnet is by default, you are attached to the surface. So if there is a power failure or anything, you will not fall. And also, you don't need to spend a lot of energy in trying to stay put. You only need a bit of energy to decouple your feet and move forward. Now, what happens if the surface that we walk around does not have suitable adhesion? So anytime we are dealing with real-world environments, we come across environmental structures which have lack of adhesion, either because the materials is not ferromagnetic, there has been some kind of layering or protection over that which reduces the magnetism, or the paint thickness itself is big enough so that there is larger air gap between the magnet and the ferrous substrate, so that the magnetism actually becomes low. So to enable us to ensure that each of the footsteps has robust contact, what we have tried to do in our project is to look at a combination of different modalities of sensing. So one of the modalities is an inductance sensor, which actually measures the change in EMF when the magnetism changes. And we have in this case, we have an IMU on board, but in some of the other results that I show you, we don't have an IMU. So as soon as you have an IMU on the feet, when the robot makes contact with the surface, you will get a signature to say that, well, there is a jerk. Based on that jerk, we can actually create a decision tree where if the contact is made, we can evaluate whether that's magnetic, whether that's a ferrous contact or not. And then if it is a ferrous contact, we can actually do a so-called pull test. What I mean by pull test is once the robot makes a contact on a surface, it actually pulls its leg apart to see whether or not there is sufficient magnetic adhesion to allow the latching to happen. So in the picture on the top, you would actually see the top right limb of the robot stepping on a cardboard box, which immediately, so even though the contact detection is being made by the IMU, the inductance sensor is saying that it's not a ferrous surface, so it's being rejected. And then the robot actually searches in the neighborhood to figure out what's a secondary useful point to search for. On the bottom video, you would actually see that because of the geometric constraint of the bolts on the surface, it creates a surface which is no longer planar. And when it steps on the bolt, it does not get a good contact. And by running this decision tree, we can actually catch this spurious contact levels and then do a neighborhood search to ensure that whenever we have a stable contact, we can trust it and then start letting the other legs go. So having this kind of multimodality in detecting the contact mechanism, we are able to ensure that at least for some scenarios, we can trust the adhesion. So in addition to the robust contact, we also, in a confined space, we are very much limited by the environmental free space. If we were to move on some kind of trusses or discontinuous surfaces, we would need some kind of sensing to tell us what are the suitable surfaces that we can step on and what are the surfaces that we can't step on, or where is the air gap. Now, if we have a single sensor which is sitting on the body, we found that for these kind of robots which are really close to the surface, we find there's a lot of occlusion that happens of the sensor using its own limbs. So the range sensing becomes really tight. And to alleviate that, what we did was we put in two different sensors. We put in individual range sensors on a small range sensors on each of the foot. So each of the foot actually has a local view of the area where it's trying to step on. And we do some basic point cloud processing and image processing technique to extract feasible footholds. So I'm just going to explain the simple pipeline that you use here. So on the left, you can actually see we have two sensors. These are picoflexes, which are point cloud sensors, infrared point cloud sensors, and you can see the point clouds shown by the picture below. We can see reasonably good resolution of the boxes and the pens and the clippers and even the rope. So once we have this point cloud being processed by individual leg, we can actually truncate those point clouds into, we can segment those point clouds into suitable, based on some kind of proximity measure, into chunks of planes which are consistent with each other. So on the left, on the middle picture, on the pipeline here, we look at the first picture, it shows the point clouds that has been generated by a single sweep of the leg. Once we run a processing pipeline, we see that these are segmented into some kind of noisy but consistent points. So the blue, the pink, the red, these show different surfaces that was segmented. But we also see that there are surfaces, for example, we do get some spurious segmentations in the form of the green edges and then the other teal edges here. Now, once we have a region that we can identify that is suitable for us to explore our foothold, what we then do is we decimate those regions into sample query points. On the rightmost figure, we'll see that we have individual points, blue points, where the robot has identified suitable point of contact that the robot hypothesizes that if it's able to put its foot on, it should be able to get a good contact based on the geometric feature. Of course, we have no idea what the ferrous features are. Sorry, what the adhesion measure is, whether or not it's a good adhesive structure. But that comes by running the adhesive evaluation that we mentioned previously. We can also see that based on our direction of motion, in this case, the robot is commanded to go up. We can actually grade this sample points in a hierarchy. So we, based on some kind of heuristics, we evaluate the sample points on the utility of the robot in performing its task, in this case, moving up, in addition to having a stable foothold on the plate. So you can see in this case, the green point has been selected for first evaluation, which is the current evaluation that's going to happen. But it has also graded a sequence of hypothesis of suitable points that it will evaluate if the green point turns out to be spurious. And the lowest valued point that it wants to sample is the point on the second plate at the bottom right, because it does not really aid in the robot's locomotion. So even though in this case, the robot does not necessarily know the full structure of the environment that it's walking across, locally it can make a decision on where its limbs should move so that the robot is able to move towards its goal. So having a simple local perception allows us to do these kind of local decision. Now, the advantages of having these local decisions running at either onboard processing or on an embedded computer inside each of the legs is that the complexity of the planning becomes low. So if you allow individual legs to make their own decision in determining where the contact points are going to be and where the legs are going to move, then the problem of locomotion becomes a much smaller subspace, a smaller dimensional problem where we need to worry about where the torso is moving, and then we can allow the legs to sort itself out once the torso has decided to move in a certain way. So you can extrapolate this thought into thinking that you can actually have distributed sensing and distributed intelligence on each of the legs and the torso, which are doing something which is optimal to their own motion, but constrained in a task level of moving the body upwards. And this is exactly what's happening on this particular video. So I'll run this in a loop, but what's happening here is the robot does not know what the environment is. So it does not know the layer of the plates, the layout of the plates. It doesn't know how many plates, what is the thickness of the plate. It assumes that it has sufficient adhesion if it is moving forward, but it evaluates each steps. So you would see the legs moving and swinging. It's trying to figure out where it can actually select a point for it to move forward. And once it does make a contact, it does a small pull test. So you would see the body actually jiggle around a bit, trying to figure out that it has made sufficient contact, sufficient strength contact. and then release the other leg. And this is what's happening at each of the legs, right? So you would see sometimes the legs stepping on the board, sometimes they fail to find a solution, but overall, because of our robust capture of errors, we are able to mostly avoid catastrophic failure. We can't completely avoid because there are other problems that we haven't really solved in this particular task. Right? So the overall goal here is once we have these kind of robots which are reasonably adept at moving, we can send this to confined space environments and do inspections for various kind of tasks. Right? So in order to do this, let me summarize what are the main challenges and what are the main science questions that we need to solve. Of course, we have the problem of sensing and perception, as I was mentioning. One of the key open problems that we are looking at right now is what is the suitable representation of the environment for climbing robots, right? How do we represent the environment? Do we actually have a geometric model, or do we actually have an adhesive model, or do we have some kind of other representation, right? I did mention that we were using a very hierarchical way of sorting out what are the failure modes that each of the sensing is detecting. But where we are moving towards in the short term is to try to fuse this into a multi-dimensional, multimodal, spatio-temporal stream from where we can learn what are good contact latches and what are bad contact latches. And then we prioritize those, as I had mentioned earlier, the range of movements, the set of points that I showed you earlier, we can actually evaluate those based on the prior information. The evaluation of the adhesion itself is also an open problem. We can evaluate the geometric structures by having the sensor on board. So we have a visual sensor. We can say, well, this is the geometry of the robot, and the robot has to move in this particular way. But often we would not be able to find out how good or bad that adhesion is, right? So if the contact is good, but the magnetic forces are weak, then it is possible that for a particular pull test, it may be successful. But as soon as we move the body in a different pose, that contact becomes really tight and weak, right? And it starts to fall apart. So the open question there is, how do we handle this? Can we detect this kind of slip happening way before it actually happens and mitigate the motion? And in addition to that, because we have active adhesive control, we have electromagnets on the feet, how can we actually increase the magnetism on the feet to ensure that our tolerances for adhesion becomes reasonably well? It's sometimes not possible because of the saturation of the magnetic field in the substrate. But in many cases, if we assume that we haven't reached the saturation of the environmental substrate, we can actually play around with the adhesive forces by changing the electromagnetic fields. And we did mention that we were looking at some of the problems related to the locomotion of the body. What I showed you was just a pure kinematic, geometric way of looking at it. But the challenges are much more complex. When we decide that we have a stable contact, we have to validate not only that particular body configuration, but the whole range of body configurations which move from the start point to the end point in a smooth fashion, right? So it is possible when we do sampling, we come up with samples which are all valid, but when we try to move from one configuration to the other configuration, we break the constraints. So that is something which is not very trivial in a geometric sense. We have to take into account not only the adhesive constraints, the mission constraints, the body constraints, but also the dynamic constraints. What is the maximum torque that the body can hold? Is the leg going to slip? What are the maximum frictional forces that the body can hold, right? So all these constraints in a very complicated fashion start influencing the way the body trajectory moves. And one of the open problems that we are looking at is basically looking at whole body trajectory planning and optimal and robust planning and control for these kind of systems to ensure that there's smoothness in not only the body motion, but also in the control space, so that there is less of a jerk and discontinuity. Of course, there are some discontinuities that's going to happen because primarily this robot is a discontinuous robot. What I mean by that is it's making and breaking contact. So anytime you make and break contact, your space, your planning space is broken down in different modes. But within those modes, we have to ensure that it's smooth and stable. So these are the open challenges that we are trying to solve to ensure that we have smooth, sustainable control of the legged robot while it's climbing. One of the things that I haven't addressed yet is the challenges that we failed in a field environment. Whenever we talk about deploying this kind of robots in a really in a field condition, we have to deal with the dirt, grime, greasiness of the surface. We may have some rust and corrosion, which then influences the magnetism of that environment. But you can also have some kind of iron particles which actually attach itself to the magnet and reduce the magnetic force or the adhesive force that the robot can deploy over time. Now, those kind of challenges have to be identified and addressed at runtime. And that opens up a whole new challenge of in situ machine learning and some kind of deep learning of the models of the locomotion as well as controllability of the robot on that particular environment. It's very hard to encapsulate that in a standard model. These are high dimensional complex parameters that play with each other. So we have to start looking at some kind of machine learning framework. So I'll stop here on the summary of all the challenges we have to face and all the issues that we need to resolve before we really start getting versatile climbing robots. And we are always looking for interested interns and PhD students who want to work with us on these platforms. So if you are interested in coding up something, please feel free to drop me an email and contact me, and I should be able to sort out some kind of collaboration with you. So I'll stop here and ask James for any questions that have come through. Sort out some kind of collaboration with you.
Okay. So we have one question here from Raghav. Sorry, do you mind? I think the stream is still unmuted on your laptop. We have a question here from Raghav. What sort of motion planning framework is used in autonomous climbing? Is the CSIRO pod controller capable enough? And what about the trajectory optimization formulation like Romula used? Like Romula used.
So let me go back to the
Simulation like Romula used.
So the first part of the question was basically what kind of motion planning frameworks are being used. So we are using different frameworks to do different tasks. So the motion that you see here for most of the robots here, they are open loop control. We are not doing closed loop control yet, but we are working towards that. The way we do the open loop control is we look at basically the foot tip configurations that we actually command the legs to move towards, and we solve an inverse kinematics. We solve the inverse kinematics problem to figure out where the joints are going to be. Once we know what the joints are going to be, we run a simple PID controller on the joint space to ensure that we actually hit those positions. So it's basically running an open loop position controller. In the future tasks, when I go, let me go to the next set of problems that next set of videos here. So for this, we are using the same mechanism. So what we are trying to do here is we are using basically dynamic cells, and the dynamic cells have, we have an SDK which controls the dynamic cell to a particular position. But on top of that, what we are doing is we are trying to figure out what is a suitable leg movement that will allow a reasonable smooth motion, right? So we use a Bezier spline to ensure that the legs are detached and move to one of the contact points. Bezier allows you to have a smoother configuration. And overall, all this code is actually written in ROS. So we do use a lot of ROS. Most of our platforms are ROS-based. So in terms of the software architecture, we use basically sometimes an action subscriber or TCP/IP broadcast kind of mechanism. In this scenario, we have an overall body locomotion planner, which identifies the direction that's being commanded for the robot to go to, and it converts that into a desired velocity for the body. The desired velocity is then converted into feasible foothold positions where the leg is supposed to step on. And to enable that foothold position, what we are showing here is individual legs move around and create a scan of the environment. The way we are actually running the scan is basically using modeling each of the limbs as a manipulator. And once we treat it as a manipulator, then it just becomes a simple task of solving the inverse kinematics of the tip position that we are controlling. So we are planning in the Cartesian space, converting that into joint space, and controlling the joint space in a position framework. Second question was, how does this compare to Romula? I'm sorry, I'll have to look up the Romula framework, but if you can drop me an email regarding the specific software that you're talking about, I should be able to respond to that. And I'll drop a response on the YouTube comment channel as well, so that anyone who is listening to this can get my answer. And I'll drop
I have a question here from Mango. Could you please say again the name of the controller or controller?
Name of the controller?
I have a question here from Yes. Could you please say again the name of the controller or controller?
Name of the controller?
I have a question here from Yes.
So it's a PID controller. So what we are doing is we are evaluating what are the positions that the leg has to be, and then we run a PID loop on each of the joints to ensure that that position is actually achieved. So we are running a PID controller on each of the joints. To ensure that that is.
Okay, cool. Alright, well, thank you so much, Dr. Tirtha, for your time tonight. We really appreciate it and hope everybody learned something. That's all from us tonight. Thanks for watching, everybody, and we'll see you next time.
Thanks, everyone. Thanks, James, for inviting me. And if you have any questions, please drop me an email. at tirtha.bandy@gmail.com. Yeah. Thank you.